Okay, it's doing it. All right, so today's lecture, what we're going to do now is we've talked about the mean field theory. We're going to now talk about the fluctuations about mean field theory. So what we're getting to is an understanding of correlations in systems with continuous symmetries. And so what I'm going to do today is I'm going to show you how to do Gaussian fluctuations in a very, very fast way to derive all the results without having to do something very complicated. And so what we're going to use is nothing more complicated than what you've already seen in your elementary statistical mechanics courses, namely the equipartition theorem of energy. How many people here have seen the equipartition theorem of energy? You guys not? You know what it means, right? Yes? Equipartition of energy, you know? You may know it by a different name, so but this is the official name, equipartition. Heard of it? Have you heard of it, Chan? Yeah. You haven't heard of it, but you need to learn it. Okay. Well, somebody who knows what it is, tell us what it is. So Chan, why don't you go ahead? Before you look on the Wikipedia.
Not quite sure.
Okay, so you don't know. Okay, all right. So you want to know what mine?
Yeah. I'm trying to remember.
Okay, so you don't know. Okay, so do you know?
Yes. So is it like the average degree of freedom have the same amount of time?
Something like that. How much energy?
1/2.
Oh yeah.
Right. So it says.
I knew that.
Yeah, sure. Yeah. That's like when I hear a guitar solo by Joe Bonamassa, I say, I could have done that. Okay. So the idea is that every degree of freedom has that. But that's not really true. That's not correct. So anybody want to correct it?
Yeah, I believe that's only true for quadratic degrees of freedom.
Right.
And if the degree of freedom has in the Hamiltonian has some power alpha.
So let's not worry about that.
Okay.
So if I have a degree of freedom, so what is the actual statement of the state of
For a degree. So in terms of like a virial theorem, for example, the average potential energy of each individual particle should be equal to 1/2 kT.
Okay. So if I have, basically if I have a Hamiltonian which is made up of a bunch of degrees of freedom which are quadratic, like that, and they're classical, not quantum. This is not true quantum mechanics. Okay, then the expectation value of AI squared, its energy. We can call that energy of the degree of freedom AI. So that is 1/2 kT. Okay. So that's the equipartition theorem. Okay, we'll talk a bit more about it. Okay, so that's how we're going to compute correlation functions. I don't forget to today, but where I'm going with this is computing. We're going to do this for scalar systems, and then we're going to just do this for the continuous symmetry. What we're going to look at is the susceptibility tensor, which is now going to be a tensor. And the reason we're going to be looking at this is what we're going to see is I'll tell you what the amazing result is. We're going to see that the longitudinal correlations have exponential decay, just like scalar systems do, but the transverse correlations have power law decay for any temperature below the critical temperature. You don't have to be at a critical point in order to have a power law behavior. So that's what the calculation we're going to get to. We're going to see that these things come from Goldstone modes, which we talked about last time, as originating in the degeneracy of the ground state of the system. And and we will get to a computation of the rigidity of the system. Okay, so before we do any of that, I need to remind you what a Fourier transform is. Okay, anybody here not heard of a Fourier transform? Okay, few. Okay, right. Here's how you define Fourier transform. This is how I'm going to define it. Okay, I'm in the box with volume V. I have a function e to the r. It's going to be a periodic function. The volume of V is finite. We'll call it L to the D, where D is the spatial dimension. Fourier says that if I write down e to the r as a discrete sum of k vectors, like this, and we'll say what this sum actually means in a minute. So you take the Fourier components on d phi k dot r. If you know what these e to k's are, that gives you e to the r. Similarly, if I want to know what e to a k is, given e to the r, what I do is I do this inverse Fourier transform. So this is Fourier transforms. Okay, now there's two things that you need to know about Fourier transforms, and that is what a delta function is. How many people here know what a delta function is? Okay, do you really? Okay. Okay. Well, so what is the difference between a Kronecker delta and a Dirac delta?
Well, the Kronecker delta is based on like orthogonality, where the indices, if they're the same, it's 1. If they're not, it's 0.
Yep.
And the Dirac delta is like a Gaussian with 0 standard deviation. It's basically a spike wherever the inside of it is 0.
That's right. It is the limit of a Gaussian. That's absolutely true. It's a generalized function, and you have to think of it in that limit. But it's also exactly the same thing as a Dirac, as a Kronecker delta. Okay. So the only difference is that when the labels are the same, it equals infinity rather than 1. And when you integrate over it, it gives you 1. Okay. So I know you're a mathematician, so I'm going to write a statement in quotation marks, so you know that I don't really believe it. Okay. All right. So there's two things you can do. So you can take this e to a k, and you can say, well, if that's what e to a k is, I substitute it into here. Okay. Now here's the thing: if I asked you to do this right now, I guarantee you at least half the class would get this wrong. And the reason is because you have to remember that in the left-hand side here depends on k. It doesn't depend on r. So I can call this r anything I like. I can call it r, I can call it r prime, I can call it hippopotamus, elephant. It doesn't really matter what this variable is. Similarly here, the left-hand side depends on r. It doesn't depend on k. K is just a dummy variable. So I could call k, or I could call it k prime, or I could call it hippopotamus or elephant. Okay, right. So now what happens when I substitute this into here? So now I've got e to the r is writing this straight away down, and then here on the left-hand side I've got this r. That r is the same as this r over here. Okay, so when I substitute an r into here, I have to make sure that I call it a different name. Let's call it hippopotamus, but that's too long to write down, so I'll just call it r prime. So I have e to the r, there's the r. This is not the same r as this. This is just a dummy variable. Okay? That's the thing that you'd all get wrong. You'd all write this down as r, and then you'd have complete nonsense, and you would get confused. So you plug this into here like this, and now you see that this has the form integral dvr of r prime of something times e to the r prime. And so you say, well, that doesn't make any sense. The only way that can happen is if this stuff is equal to a Dirac delta function. The Dirac delta function is 0 when r is not equal to r prime. So it's like orthogonal, just like you were saying, in terms of the argument. It's 0 when r is not equal to r prime. It's equal to infinity when r equals r prime in the generalized function sense that you said, of Gaussian, whose width gets smaller and smaller, but whose height gets bigger and bigger. That's the thing, okay? So that the integral of the Gaussian always stays the same. As the width gets smaller, the height gets bigger. The more dangerous the enemy, the sharper the sword, okay? And then the end result is that its integral is equal to 1. Okay, so therefore I can read off that this stuff is a delta function. And so I read off that 1 over v sum of the k, here's the ik of r minus r prime is equal to delta of r minus r prime. And if you had done this before I reminded you about dummy variables, you would have got r and r here the same, and then everything would have made no sense. You would have got 0 equals 1 or something like that. Okay, so that's a Dirac delta. Now, when we do that, when you look at this, you say, well, that's not what I remember. I remember when I did calculus that the delta function, delta of x, was just 1 over 2 pi e to the I kx. Right, that's what a delta function is. At least that's what you learned in your mother's knee. And it doesn't look anything like that formula, which has got sums and stuff like that in it. So let's see why not. So when we write down the sum, well, remember that the k vector is 2 pi over L nx ny nz. In 3 dimensions, if I'm in d dimensions, 2 pi over L n1, n2, n3, blah, 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 all the way up to nd, and n's are integers. Okay? So let's suppose I want to look at a volume in k space, integral d dk. This is the measure in k space, d dk. That's dk1, dk2 up to dkd. Just like d3r is dx, dy, dz. So this is just a generalization of that, but it's in k space, not in real space. So now I can read off from this, since k is equal to this volume element, k space is 2 pi over L to d, dn1, dn2 up to dnd. And each of these dn's, those are changes by integers. These are summing over integers. So when I write down the sum over k, what I'm actually doing is I'm summing over these integer values, which come from the periodic boundary conditions. n1 can 1, 2 up to infinity, and 2 is up to 1 to infinity, blah, blah, blah. And so that I can write from Euler-Maclaurin theorem as basically dn1 up to dnd. And so then if I just do the change of variable here, and this is the part which is, of course, is slightly sloppy, then all the sum of the k is L over 2 pi to the d times d dk. And so therefore, now I plug this into here. The sum of the k is 1 over v, and then v over 2 pi to the d, d dk, blah, blah, blah. And the v's cancel, and then this thing is just the integral representation of the delta function that you learned on your mother's knee. Okay? This formula here has a name. This thing is known as the density of states in k space. So let me write that down, because that's what I'm always going to call it. This applies whether you're doing quantum mechanics, the quantum numbers, or you're doing modes of the electromagnetic field or some other field. I've got a bunch of modes. I label the modes by integers, right? They're standing waves, 1, 2, 3, that tells you how many nodes there are. So these are integers. And then the k vectors associated with them are given like this. So this tells you if these are the numbers in the nodes in the mode space, the density of states, which is just the transformation from n to k, is this factor over here. So this thing over here is L over 2 pi to the d. That thing is known as the density of states in k space. Okay. All right, so that's so indeed. Now that's what a delta function is. We've learned the resolution of unity. Now let's do about the other thing. This was substituting 2 into 1. I took this e to k and stuck it into here. Well, you could say, well, why do that? Why don't I take this e to r and stick it into here? So I can do that too. So let's do that. So e to k is equal to integral ddr e to r e to the I k of r. Where is the dummy variable in this formula? What's the name of the dummy variable in this formula? What? I couldn't hear you.
Oh.
No, k is not a dummy variable. Did you say k? This equation reads as follows. Give me a k value. I'll tell you what the value is of e to k. So I put the k in here, and that k comes in over here. So which variable is the dummy variable? Oh, exactly. Oh, it's just integrated. The answer doesn't depend on r. I can call it hippopotamus. We'll call it r prime because it's easier to write. So So I write integral ddr e to the I k dot r. And now what I'm doing is I'm making a sum. Wait, which way am I going? I'm substituting. Well, I'm substituting 1 into 2. I said 1 way. I'm substituting this one into here. Okay. So in this one, k prime is the dummy variable, and I'll call it k prime. So here it is, sum of a k prime, e to a k prime, e to the I k prime dot r. And this is then just stuff times e to a k prime. So the stuff must be the Kronecker delta, which is 1 when k is equal to k prime and 0 otherwise. And so I can read off the v delta k prime is equal to integral ddr e to the k minus k prime dot dr. Okay, and they say, well, is that really true? So let's think about it, what it means. Let's set k equal to k prime. I said k equal to k prime, this thing is 0. So I've got e to the I 0, that's just 1. I've got the integral over the volume of ddr, that gives me just the volume. So that gives me v delta k k prime, when k is equal to k prime is equal to v, so delta k k prime is equal to 1. And so I get that, so that works. If k is not equal to k prime, this thing is the integral of a bunch of sines and cosines, and they're going to average to 0. And so what's going to happen is I'm going to get the right-hand side is equal to 0. So this is a good representation of the delta function. Okay, so that is how you do Fourier transforms. And then there's one last thing that we can say. So there's one last trick. So what I've got is that the integral. If I look at this formula over here, this one over here, I don't want to ruin this formula here. So let's have a look at that in the limit as v goes to infinity. So I've got the integral d dr e to the I k minus k prime dot r. What?
It should be a k prime, not r prime.
Thanks. That is equal to v delta k prime. So that's what that's what I just proved to you. So let's have a look at what happens in the limit as v tends to infinity. So if I look at what I showed you before, that 1 over v sum over k e to the I k dot r minus r prime. So that thing is equal to delta of r minus r prime. And so this thing is equal to, using the density of states in k space, 1 over v times v over 2 pi to the d sum over k e to the I k dot r minus r prime. So that's delta of r minus r prime. So I can do the same thing with k's and k primes. So now let's swap r to k. So then what happens up here to this equation, the star, I can write the swap as this: e to the integral of ddr e to the I k minus k prime dotted with r. Well, that thing is going to equal 2 pi to the d times delta of k minus k prime. Okay, so all I did was I said, if this is true, then I can just do the same thing in k space rather than in r space. And so what that means is a very strange result, which is kind of cool. And what it says is that in the limit, v delta k and k prime gets replaced by 2 pi's of the d times delta of k minus k prime. So this means that if I start off by thinking of systems on a lattice, which is very easy to do, everything is discrete. Everybody hates discrete sums, so you always want to turn something into an integral. So the rule is wherever you see a v delta k k prime, you just replace it by 2 pi to the d times the delta function. And that's the last bit of Fourier transform magic that we need to know. Okay, so now let's do some physics.
Sorry, in that line right before you say swap r to k.
Yeah.
You introduce the density states v over
Yes,
2 pi to the d.
yes,
And then should that be then an integral and not a discrete
yes,
sum?
yeah, it should. Yeah. Okay, so let's now go and start doing some physics. So now I want to talk about going beyond mean field theory. So what we're going to look at is small fluctuations about the mean field value. And the physical picture that you should be having about this is the following. So let's suppose I have some order parameter. I'll just call it phi, just for no good reason. I've got some potential like this. It's fluctuating about the mean field value. So there's the mean field value. And now what we know is that actually the real thing is going to be fluctuating. So if I were to look at it over time, it would start, say, over here, and it would be sort of fluctuating back and forth in this well like this. So if I looked at phi as a function of time, what I would see is that there's some mean value. And then about that mean value, the system is fluctuating like so. And what we want to know is what is the contribution that those fluctuations make to the thermodynamics. Okay, so that's the question that motivates everything we're going to do. So let's start it off by looking at 1 degree of freedom. So what I'm going to do is we'll look at 1 degree of freedom, and it'll be pretty simple. Then I'll do n degrees of freedom. It'll be slightly more complicated, and then we'll do an infinite number of degrees of freedom. So the Gaussian approximation, I've got 1 degree of freedom. Let's call it Q. Is to say that the probability distribution of Q is proportional to e to the minus Q naught squared over some standard deviation. So I want you to think of Q naught as the expectation value of this variable Q, and it's making fluctuations about it with some standard deviation sigma. Okay, so let's have a look at what does statistical mechanics tell us. So statistical mechanics tells us the probability distribution of Q is proportional to e to the minus beta times the Hamiltonian of what this variable is. And so that is going to be basically e. So what we're going to be saying is essentially h of Q is equal to h of Q naught plus 1/2 of Q minus Q naught squared over some width lambda squared. So that's the idea. So what we'll say then is that if I want to compute P of Q, that is going to be e to the minus beta times h of Q naught, and then times 1/2 over whatever is the width here, Q minus Q naught squared, plus higher order terms that we're not going to worry about because we're just doing Gaussian fluctuations. And so all I've done here is I've expanded h of q is h of q naught plus 1/2 d2h by dq squared evaluated at q naught times q minus q naught squared. And the first order term has vanished because by definition, that is the value. And so when I talk about this value lambda, 1 over lambda squared is just beta d2h by dq squared evaluated at q naught. So that's what everything means. So then the expectation value of q is equal to q naught, as we said, and the expectation value of q minus q naught squared. So I look at the fluctuations of q about its mean, I square them so that they add up, they don't add up to 0. If I didn't square them, they add up to 0. So that is just going to be q squared minus q naught squared, like that, and that is equal to lambda squared. Okay, so when I worked out the free energy, e to the minus free energy over kBt, with this 1 degree of freedom, is just going to be the integral from minus infinity to infinity of q e to the minus beta h of q, and that's just going to be e to the minus beta h of q naught. And then the only thing I have to integrate is this q minus q naught squared. It's divided by lambda squared, so the integral will be the square root of 2 pi, but there's a lambda squared in there, and so it's that times 2 pi lambda squared. So that's the factor that comes from doing the Gaussian integral. Okay. So, yeah.
Sorry, the Hamiltonian, are we already assuming an approximation at the Hamiltonian level since we started writing that down?
Yes.
Yeah.
Yes, we are writing this down and we're ignoring everything else.
Right.
So
Like even 2 lines above it, where you wrote.
Yes.
Yes.
This is the problem. I'm just explaining where this comes from.
Great. That's
That comes from taking the Hamiltonian and
Yes.
expanding it and throwing away the higher order terms. And then this lambda squared that I just wrote in here, that's defined by this. Yeah.
Just for clarification, it's e to the negative 1 over kBt.
This thing here is e to the minus the free energy over kBt.
What's the same as that?
So in statistical mechanics,
Yeah.
F, yes. Free F for Helmholtz free energy. So if you remember, the Helmholtz free energy is defined as minus kBt and the logarithm of the partition function. And I don't like that formula, as everybody knows. I write it like this: e to the minus free energy over kBt is equal to the partition function, and the partition function is the trace over whatever are my microscopic degrees of freedom of the Hamiltonian. Ignore that. So this is the thing. Okay, so that's nice, but I like to have everything in the exponential, because what we want to know is what is the free energy. So therefore I can read off that the free energy is just the Hamiltonian at the mean value, Q0, and then minus 1/2 kBt times the logarithm of 2 pi lambda squared. So the free energy gets changed by an amount that depends on the logarithm of this matrix here, this Hessian matrix. Okay, so that's 1 degree of freedom. Okay, everybody happy? Okay, n degrees of freedom. The same thing, but with n minus 1 more integrals. Okay, so now I just say, okay, fine. So Q is now going to be a vector, Q1, Q2, all the way up to Qn. And then I expand my Hamiltonian. So this is equal to H q naught plus 1/2 q alpha minus q alpha 0 d2h by dq alpha dq beta evaluated at q naught times q beta minus q beta 0 plus higher order terms that we're neglecting. And so this is now the generalization of what I have over here, just a quadratic expansion of the Hamiltonian about the mean field value. So we'll define a matrix M alpha beta is defined to be d2h by dq alpha dq beta evaluated at q naught. And then what do I do? Well, I want to compute the partition function eventually. So the thing I want to compute is the partition function. So that's the partition function z is e to the minus beta times the free energy. And now the partition function in this case is the integral from minus infinity to infinity, the product from I equals 1 to n dqi, and then e to the minus beta h of q. So that's what we're doing, is just calculating that. And I can take out the mean field value. So that is e to the minus beta h evaluated at q naught times the integral of pi I equals 1 to n. And now what I have is e to the minus 1/2 q alpha minus q alpha 0 m alpha beta q beta minus q beta 0. That's all I have. And this is a big mess, but it's easy to do because all I have to do is diagonalize this matrix. This matrix is symmetric, so I can diagonalize it. So so what we do is we diagonalize this matrix M like that. And what does diagonalization mean? Well, what we have to do is find its eigenvalues and eigenvectors and then perform a similarity transformation on that and rotate in the eigenvector space. So I'm going to define M alpha beta has eigenvectors, which I'll call V beta. They're labeled by some I, and then these have values which I call lambda I, and then I'll get the ith component, the alpha component of the ith eigenvector. So this is the eigenvector component, eigenvector definition. Let's take this vector sign out, because what we're doing here. So alpha, beta, gamma, all those Greek indices are just coordinates in Q space. So this is the eigen problem. And I'm going to define these new eigenvalues, 1 over lambda I squared, to be beta times lambda I hat. So that's a really terrible choice of notation, but that's what I did. And when you do that, then what you end up with is that the partition function is equal to e to the minus beta h q naught. So that's the mean field value. And now the integral becomes, after doing a rotation, equals 1 to n new coordinates, which are defined like that in terms of the eigenvectors, e to the minus 1/2 sum from I equals 1 to n of q I prime squared over lambda I squared. And the point about that is it's completely separable. And so So this is equal to e to the minus beta h of q naught. Now take the product sign out of the integral. And then inside here, I just have one integral d q I prime e to the minus 1/2 q I prime squared over lambda squared. And this integral is just the square root of 2 pi lambda. And so therefore what I get is that f is equal to h of q naught minus 1/2 kBt times the sum from I equals 1 to n of the logarithm of 2 pi lambda I squared. So, okay, so I went through this super quick, okay? But everything I just did here is just the n-dimensional version of what we did with the 1 degree of freedom. And all we're doing here, you have to know, if you don't know this, you need to learn this. How do you diagonalize a symmetric matrix? Because by what we've done is we've got this horrible integral over here, and we turned it into a matrix M, which is symmetrical. Sorry, which is diagonal. Once the matrix is diagonal, then it's trivial to do the calculation. So the whole point of doing this, diagonalizing this, meant that over here that M looks like this. So it's has been transformed, let's call it M prime, into lambda 1, lambda 2, up to lambda n. I call these with little hats. So it looks like this, and then everything here is 0. So this is very basic linear algebra, and I'm not going to go through it, okay? If you need to learn it, I can show you where you can look, or you can teach you how to do it, but you have to know that. Everybody happy with that? Okay, great. So now that we've done that, now we can do an infinite number of degrees of freedom. So this is going to be, formally, we would say, well, what are you doing? Here we're calculating the free energy. And now we've got our Landau theory. So I've got e to the minus beta times my Landau theory. That depends on an order parameter, which is now a function of space. And why is this an infinite number of degrees of freedom? Well, it's an infinite number of degrees of freedom because there's an infinite number of points in space. And so it's formally infinite, but of course we never actually do anything infinite. We always make it finite. And so we have to do an integral over all of these variables. So we have to do an integral over this function d eta. That is just the same thing as doing this, but just taking n equals infinity. So all we're doing is this, and people call this a functional integral. But we don't need to worry about that, because what we're going to do, the strategy, is just to do this in Fourier space. And why do we do it in Fourier space? Well, remember what we did at the beginning of the lecture. At the beginning of the lecture, we start off with a function, which is a continuous function. Then we Fourier transformed it. It had a bunch of discrete Fourier components. So now it's easier to do the calculation because I've got discrete Fourier components. So let's first of all write down what L is. So L is the following. I'm going to just do this for a scalar case. I'm in d dimensions, and then what I have is I have a half gamma grad eta squared plus f of eta, and this f of eta we realized last time is equal to a times t eta squared plus 1/2 b eta to the fourth, at least if we have a scalar, okay? So I'm going to do a calculation for you. We're going to look at what happens when we do this for t greater than tc. So if t is greater than tc, that means t is greater than 0, like so. And what that means then is that the potential just has a minimum at eta equals 0. So the potential looks like that. So therefore, the expectation value of eta, the order parameter, is equal to 0. And so what we're going to do is expand about 0. You are going to do this when I expand about the ordered phase. Okay, so make sure you understand what I'm talking to you about, because otherwise you won't be able to do anything. So here is our system. So here is our potential, f of eta. Here is eta. It looks like that. And this is true for t greater than tc. When t is less than tc, what we saw last time is it looks something like this. I've called this f, but previously we called it v. It doesn't really matter. Now what it will look like, it looks something like this. So this is for t less than tc. And this point here, or this point here, this is eta squared is minus at over b. Over 2b. I don't know why I use this language. So I've got 2 points, two minima here, and so what we're doing in the Gaussian approximation is we're looking at small fluctuations about this well, or small fluctuations about this well. So I want to know what happens below TC. I choose eta squared is this value here, this equilibrium value, and then do the expansion about it. I'm going to so that means you have to take into account this e to the fourth term. Okay, but I'm not going to do that. I'm going to just expand by e equals 0. So I just throw away that e to the fourth term. So what you will do, so for t less than tc, you expand about eta is equal to the square root of minus at over. Actually, there isn't a 2. I'm just being an idiot. Okay, there was a reason why I put that. Okay, you're going to expand about that. It can be either plus or minus. So you're going to expand about that plus some delta eta, and you'll need to include the e to the fourth terms, but only work to order delta eta squared in the free energy, in the Hamiltonian. Okay, so what I'm going to do here is we're going to do t equals t greater than tc. That's what we're going to do right now. So this is what we're going to do here, and so we expand about eta equals 0. All right, so I can write the Landau free energy as the sum over k and k prime, the integral d dr over v squared times the following: 1/2 gamma minus k dot k prime plus at times eta of k, eta k prime, these are all vectors, times e to the I k plus k prime dotted with r, and then if there's a constant piece, that will be added to this free energy. So all I've done is I've taken this free energy here, I've substituted in the Fourier expansion for eta, and then these k and k prime terms are going to give me this, and so I can write this as 1 over v um, 1 over v sum over k and k prime. Okay, now let's be careful here. So I got a half gamma minus k dotted with k prime plus at. This is eta of k prime. And now what I've done is I've done the R integral. So this is multiplied by delta of k plus k prime and 0. Right? So this is the thing that you need to keep track of. So what I did here was I did this integral first. And there's the R. And once I do that integral, remember how we expanded the delta function? That integral just gives me delta of k plus k prime. And so once I have that says the k has got to equal minus k prime. And so therefore, what I end up with is that the whole thing is equal to 1 over v sum over single k times 1/2 eta k squared, its absolute value, times 2 at plus k squared. So that is what the free energy looks like, expanding in the fluctuations about 0. Okay, so if I go ahead and do this, so let me just,
Sorry.
yeah, hang on, wait 1 second, let me find my place, because I thought this out very carefully. Okay, yeah, I can take your question.
The delta k plus k prime would mean that k prime has to be minus.
Yes, yes.
And then,
So that's why the k squared, the minus signs get cancelled, and I get plus k squared, and then k, eta of k and eta of k prime becomes absolute value of eta k squared, because eta is real. Well, I didn't tell you this, I forgot to tell you. Okay, eta is real, well, you knew that, but if you have a real function, but take its Fourier transform, the Fourier transform of minus k is equal to minus the Fourier transform of k. So it's the complex conjugate of it. So let me thanks for asking about that. So this step here, this is arising because eta of r is real, and because it's real, eta of k, take its complex conjugate, is eta of minus k. And you should check that, okay? Just as one line to plug into the definition.
Is there a gamma k squared in the final term?
Yes, there is. I just forgot to write it down. Just made a typo. Okay. So that's a gamma k squared. Yep. Okay, so let's move on from that. So then if I do the calculation, so now my e to the minus beta f is now just the product over k, the integral d eta of k e to the minus beta times 2 at plus gamma k squared times the absolute value of eta of k squared divided by 2v. And this integral can be done because this thing here is eta k real squared plus the imaginary part of eta k squared. Okay, I have a complex number z equals x plus iy, then z squared, its absolute value is x squared plus y squared. So if I've got z, so that's if z is x plus iy, the absolute value of z squared is x squared plus y squared. Okay, and this is just a variable. It has a fancy name. It's labeled by k, but it's just a variable like complex number. So its absolute value squared is just the real part squared plus the imaginary part squared. This thing here, d eta, well, if I had a vector or a complex number, dz is dx times dy. And so this thing over here, I can think of as this integral, is the integral from minus infinity to plus infinity, dx dy eta minus some constant times x squared plus y squared, and that is pi over a. Usually if I have a Gaussian integral, it's the square root of pi over the thing, but here I've got two integrals, they factorize, until I get that. And so now if I substitute this in, then what I end up with then is free energy is equal to whatever it is at the constant value, the value of F at when eta is equal to 0, which is just some number, and then this whole integral here is just going to be just like we had before, minus 1/2 kbt times the sum over k values of the logarithm, or whatever I've got in here. Whatever I have in here is this big mess over that. That's just the lambda like I had before. So that is reads off 2 pi v times kbt divided by 2at plus gamma k squared. I've got a sum over k here, but that's not quite correct, because remember that this Landau free energy is a coarse-grained free energy. As we described before. So only has long wavelength Fourier components. So we've defined some cutoff, and so we'll say that the absolute value of k should be less than some coarse graining scale in momentum space or k space, which we'll call lambda. So that's what this sum over k is. That sum over k is restricted to the absolute value of k being less than lambda, which means the long wavelength of the system. So that's the free energy for a system where it has an infinite number of degrees of freedom. It's ordered about some average value. It's now making small fluctuations in space as well as in time. And I'm looking now, if I average for long periods of time, so I do the equilibrium statistical mechanics of the system with spatial fluctuations, what is the free energy that I get for that? And the answer is this, as long as those fluctuations are small. This is just the generalization of the formula that we had over here for the n degrees of freedom. It's just that these lambdas are this formula, something like this. Why? Because the eigenvalues now involve k, because the matrix that comes in here that diagonalizes this is diagonal, but the coefficients of these, of any mode k that you want to mention, any mode k has as coefficient 2at equals gamma k squared. So these lambdas here in this formal thing actually are related to the wave number k in this thing. So this is from this, if I know the free energy, I can now work out the heat capacity, I can work out susceptibility, I can work out anything I want from this formula. Okay, so that's the free energy, but I don't care about the free energy. Okay? I care about the correlations.
I was gonna ask this, was this, I forget, are we above TC?
Yes, above TC.
Okay, just
I said so. Right here. Yeah. So I just expanded above TC, but but you guys can do the expansion below TC, and the only difference is going to be that you are going to expand not about zero, but about the solution of the steady state equation above TC. So you're going to expand about this value here or this one here, whichever one you like. So that value is minus AT over B. T is negative below TC. So you're going to take this, substitute into here, and you're going to get exactly the same formula that I got. But there's going to be one difference. Everything is going to be the same, but this number here will change. Okay? And if I remember right, this number changes to a 4. Okay? Everything is exactly the same, but there's a slight difference. That slight difference is reflected when you expand this and put these terms in. You will see that you get a slightly different formula. And what that slightly different formula means, for those of you who took my course last quarter, what that means is that you have a correlation length, which is the same temperature dependence below TC and above TC, going as 1 over the square root of T minus TC, but the coefficient is changed by a factor of root 2. And you'll see that when you do this calculation. Okay, so now we've done that, now we're going to talk about correlations. Actually, let me just check that this is what I want to do. Okay, so what have we done? We did this, we did this, we did this, we did this. Now I want to tell you about correlation functions. Okay, now I'm going to show you a really cool dirty trick. So next thing we want to do is compute 2-point correlation functions. So what we're trying to ask ourselves is the following question. If I'm sitting at this point in space over here, and I look at this point in space over here, and I measure what is the order parameter doing around here, what I want to know is what is the order parameter doing around here. I want to know if this thing is, if the order parameter is sort of positive over here, is the order parameter positive over here? Is it the same value? Is it going to be a different value? Is it going to be opposite value? Okay, so I want to know, conditioned on this, what is the value over here? That's what we can predict from the correlation function. So what we do is I'm going to show you how we get that. I'm going to show you how we get it in a very interesting way. Okay, so that's the question. We want to understand our goal. Our ultimate goal is to understand how spatial correlations vary with distance. And so we will end up computing something that looks like this. It depends on 2 variables, and it's going to depend on eta at r minus the average value of eta at r times eta of r prime minus the average value of eta of r prime. I don't know, why do I always write these things badly? This is an important equation, so I'm going to write it again. Okay. So this is the things I want to compute. I can think of this. This is delta eta of r is eta of r minus its average value. Okay, and this thing is what we call the fluctuation. It's the fluctuation about the mean value. So what this g of r is doing is g of r minus r prime is looking at the fluctuation at point r and the fluctuation at R prime. And this function g is going to be big when both of these things are the same. It's going to be small when this thing has nothing to do with this. So when I average over it, they're going to be decorrelated. So note that eta of R, its average value is the average of eta of R minus the average of eta of R. Well, the average of eta of R is a number, 3. So the average of value of 3 is what? 3, okay? So this thing is equal to 0. So therefore, if these things are uncorrelated from each other, this will just factorize into two things whose expectation value is equal to 0. So this g of R minus R prime is small, basically 0, when delta eta of R and delta eta of R prime are uncorrelated. In other words, g of R minus R prime will equal delta eta of R expectation delta eta of R prime. Neither of those things depend on R and R prime, and they'll give you 0. So it's large when they're correlated. So that's what the thing that we want to calculate. So how can we do that? Well, we can do it by a beautiful little trick. So let's have a look. So here's the trick. And the trick is to use the equipartition theorem. Why can we use the equipartition theorem? Well, let's have a look at what the Hamiltonian looks like. Here is our Hamiltonian. Here it is, right down here. This Hamiltonian, or this effective Hamiltonian, this Landau free energy, whatever you want to call it, it depends on these etas quadratically. Okay? This order just depends on these quadratically. So this is just like saying I've got a spring and the energy is a half kx squared. Here the energy is this little thing, where it depends on k, but this is just, k is just a label for this particular variable. So the effective free energy, the Landau free energy is quadratic in the eta k's. And so I can say straight away that so I know that our L, which is our effective Hamiltonian, is just what I wrote down over here, is the sum over k of what? 2at plus gamma k squared over v. There's a half times eta k squared. It's just equal to that. That's what our Hamiltonian is. And so what I know is that every term in this Hamiltonian has expectation value kt. Every term has average value of a half kBt in thermal equilibrium. So therefore, I can just read off that expectation value of eta k squared times 2at plus gamma k squared over v, that is equal to 1/2 kBt. Right? Wrong. Okay? It's not that. There's something missing. What's missing? Look over here. When I say absolute value of a variable, I mean the real part squared plus the imaginary part squared. So what's missing? How many variables is this? It's 2. It's the real part of eta k squared and the imaginary part of eta k squared. So this whole thing doesn't equal to a half kBt, it equals 2 times that, right? Because this thing here is because I'm summing over the real part of eta of k squared plus the imaginary part of eta of k squared. And each of those has a value of half kT. So therefore, so now I know that I've done the calculation. I've just computed that eta of k squared is equal to kBTB over 2AT plus gamma k squared. Okay, so you say, well, fine, but who cares about that? Well, I'll tell you why we care about that. Let's write down, let's Fourier transform this. So we have a formula that says what eta of k is. So the expectation value of eta of k squared is equal to the following. Eta of k is the integral of e to the I k dot x times eta of x. So this thing is equal to the integral d dx, integral d dy, e to the I k dotted with x minus y times the expectation value of eta at x. Why does it keep doing that? Eta of y, and that's what it is. What I did was substitute in for eta of k the definition, the back Fourier transform. Since it's the complex conjugate, it's eta of k times e to the, it's eta of k times eta of k star. Eta of k star has the minus sign because eta is real. And so this minus sign here comes from the fact that this thing is equal to eta of k times the complex conjugate. So the minus sign in x minus y is because eta of k squared is equal to eta of k complex conjugate, which is eta of k, eta of minus k. Okay, so this thing then, so now let's go back to our formula. So what we've just derived is that the expectation value of eta of k squared is equal to the two integrals of this. Okay, let's do this. So let's do the outer integral first. So let's set y equals 0. So set y equals 0 here. Okay, so ignore that. If I do this integral d dx e to the I k dot x times this thing, y is equal to 0. This thing is just the Fourier transform of g of r. So if I set so this thing is equal to v times the Fourier transform of g of k. So again, the reason is that the integral d dx times the integral d dy e to the I k dot x minus y eta of x eta of y, like that. So this thing over here is g of x minus y. because that's what I wrote over here. That's how I defined this correlation function. Expectation of eta is 0, let's say, from above TC. So the thing that I've written down is equal to this. So let's set y equal to 0. Then the integral dx of e to the I k dot x g of x, that is just equal to the Fourier transform of g of k. By definition, it's just a Fourier transform. Now, I just set y equal to 0 here, but I could have put y anywhere in this plane, anywhere in space. This number is independent of y. So therefore, so now when we do the integral dy, that just gives you a factor of v. And so therefore, what I've shown you is that this calculation of expectation value of e to k squared is equal to v times the expectation value times the Fourier transform of the correlation function. So now I can just read off that the correlation function in k space is equal to kbt over 2at plus gamma k squared. And I can write that as kbt over gamma times 1 over k squared plus k is dimensions of 1 over length. So this is a length to the minus 2. I'll call that length psi greater than, and psi greater than correlation length to the minus 2 is equal to 2at. So that tells you that the correlation length above the transition goes like 1 over 2at to the 1/2 power, which is what we saw last quarter when we were looking at phase transitions. So this thing here is the correlation length. Because k has dimensions of length to the minus 1. Okay, so what does that tell us what the correlation function looks like in real space? So in real space, eta of r prime looks like this. It's 1 over v squared sum over k and k prime e to the I k dot r plus k prime dot r prime eta of k prime. And then I have to put angle brackets around that. And so that thing is equal to 1 over v sum over k kbt over 2at plus gamma k squared times e to the I k dot r minus r prime. So that's how we've calculated the correlation functions. Okay, now I know this went by super quick, okay, but all I did was just the equipartition theorem plus the Gaussian integrals that we had done at the beginning. So this thing, by the way, if you look at it, what we just showed was that g is a function of r and r prime actually is equal to g of r minus r prime. In other words, translationally invariant. It's translation invariant because it only depends on the distance between points in space. It doesn't depend on where those points are. In thermal equilibrium. Okay, so I think I should stop here. There's one other thing that one can do, which I'm not going to do. We'll talk about it the next time. Let's see how far we got. So we got up to here. So we did this. We did that. And what I didn't tell you was about the static susceptibility. So we'll talk about that. That's just one line. And then next time on Wednesday, we'll start off by doing the generalization list to systems of continuous symmetry. So before then, please take a look at the algebra that I did. It's not important that you can replicate every factor of 2 and so on. Okay, although it's it's great if you can, particularly if you're going to do a homework set. But I'm going to make the homework sets as short as I can. But you want to understand the logic here. The logic is just putting together a bunch of things that you all know and just presenting them together in a way that you probably haven't seen before. Even those of you who took the class last quarter, where we did calculate correlation functions, where you saw that it was calculated, you haven't seen this way of doing it before. So everything in this class is orthogonal to what we did last time. So you didn't see this last time either.
No.
Yep. Okay. Any questions about today's lecture? Yeah.
So for the expression for the free energy of the infinite degrees of freedom.
Yes.
Yeah, so this one. So there's a sum like over k for k less than lambda. So I wonder if the sum should only take half of that space because
Yes. You're right. Okay. So if you did this, suppose I asked you to actually compute this number, okay, which you can do. So homework exercise, but I didn't want to give it to you to do. You would turn this sum into an integral, right? And then you would say, but wait a minute, eta of k and eta of minus k are related because one is just the conjugate of the other. And so what you would do is you would restrict k to being the upper half plane with only integrated over half of k space. That's exactly right. That's your question. Right?
or can we just add a 1/2 factor?
You can just stick it at the factor 1/2, but make sure you know where it comes from. Yeah.
So we should add a 1/2.
Oh, in this formula, well, yes, I guess you can. So let me just make another note that in fact this sum over k less than lambda is only over kz greater than 0 because eta of k and eta of minus k are not independent. So yeah, so that's some. I think I normally write it down with a prime. And in fact, in my book, I noted this. I call this sigma prime. And I said
It's arbitrary which half plane you do it over. It could be kx, ky, kd, whatever.
you can do whatever you want. You can make it the most complicated thing you like. So you can just stick an extra factor of half and do it over everything. Okay, as long as you know, I mean, this you have to make sure that you understand the symmetry of the order parameter. So yeah, you're exactly right. Good, thank you for commenting on that. Any other questions? Yeah.
The when we looked at the fluctuations, sorry, the correlation function being fluctuations at r times fluctuations at r prime. What if they're anti-correlated? Then it just becomes largely negative. That also.
Yeah. Mm-hmm. Yeah. So they're still correlated, right? But negatively.
Yeah.
Okay. No other questions? Okay. If anybody has you know, in this class, we talked about a lot of things that were background things. Some of you may not know. I will look at my schedule now that it's somewhat crystallized and figure out when my office hour will be, and then you can. But anyway, don't wait for my office hour. If there's something you want to ask, even if it's elementary, do it in Teams, okay? Because as many of you know, I will reply to Teams even if it's like a midnight or something like this, okay? So just do that, and do it in the you know, ask. You can just send me an individual chat, but I guarantee you, if you've got a question, other people in the class will have the same question. So do it in the post lecture, or if I want to send you homework 1 in the homework 1 chat or in the general chat, so that other students can see it, and also if other students want to answer the questions, then they can do that also. Okay, so that's that for today.
One quick question. That correlation function that the G of R prime